Welcome. In this lecture, which has multiple sessions, we'll explore Newton's method and a method that's called scaling. The main concepts for this lecture are that we're going to take the local quadratic approximation we had for functions that have a scalar argument, and we're going to explore them for functions that have a vector argument. This will lead us directly to Newton's method. We'll refer to damp Newton's method as Newton's method where the step size is selected using backtracking. We'll begin by looking at scaling, and we'll discover that this is a way of doing a steepest descent in an altered fashion. One sample problem that we can explore here is suppose that we have a deep and narrow valley in some data, and we want to get to the bottom of that valley. For example, suppose we're given a quadratic function, and this particular quadratic function is one that I wrote down, and here we have, so it's a second order function. The second power is the highest power of that's involved, and we can write the gradient down simply by differentiating this with respect to W1 for this term. I put a comma in here for clarity, and then this is the derivative of that function with respect to W2. We then compute the Hessian, and we see that the Hessian is symmetric, and in this case it's positive definite. And I know that because I can do the solution for it fairly straightforwardly. So what we observe is that this Hessian is positive definite, and that means that the function is everywhere convex, which makes sense because it's a quadratic function. We could look at a surface plot of this. If we do, we see now what I mean by a deep and narrow valley. If we start along here, we're in a deep, deep valley, and then that deep valley has a shallow minimum over here. So that's the behavior, geometrically, of the function that we're going to look at. If we try some previous quadratic function and this quadratic function using the backtracking method of previous sessions, here's what we see, is that the previous quadratic function, the backtracking method approached the minimizer fairly directly. Now what we see is that the backtracking function will take one immediate step in the steepest direction, it'll drop into the valley, and then it's oscillating slowly towards the minimizer. So this valley, it takes one step to get into the valley, and then it takes 100 steps along the valley, and the backtracking algorithm oscillates as it does so.